All right. So back in the day when math textbooks were physical books and you had to read stuff on the page, they would sometimes write an exponential expression and then they would put logarithms inside the exponential. So you've got your 9, and now you've gone up to the superscript, which is smaller, and then inside the superscript, you put something with a subscript. So, yeah, those threes. Apparently, those little tiny specks are threes. But I can definitely say I've been living in the age of modern technology too much when I've taken physical paper and like pinch zoomed and like, oh yeah, this is paper. That doesn't work. So that's one of the nice things about doing digital homework is if you can't read something, you can make it bigger. Didn't work so well in old textbooks. In fact, really old textbooks, like there were symbols that weren't on the typewriter. So they would have like this typed thing, and then somebody would hand draw in a symbol on the page. So they'd have to do that for every version of the book. Like, yeah. Or some textbooks like used e to the power so much that they were like, we're just going to write exp open parentheses because everything we're typing off after is so convoluted that, yeah, we can't type that all as a superscript. So if we write exp parentheses, that just means e to the, and just remember. So what we're going to take a look at some today is exponential equations. We probably won't get into the logarithm equations just yet. Before we do that, though, are there any lingering questions on any of the open homework or the writing assignment that's due next week? Um, yeah, any of that. All right. So exponential and logarithmic functions show up all over the place. So population growth or decay functions, radioactive decay like carbon dating, and even some financial interest. So we'll have an equation that either starts as an exponential or a log equation, and we're wanting to solve for the variable in there. So we have to know how to use exponential and logarithmic functions together, how they work as inverses to solve these equations. So here's our first exponential equation. And we have written to the side here, this is the one-to-one property of exponential functions. So for any algebraic expressions S and T, so for whatever crazy algebra mess S and T are, and any positive real number B, as long as B is not 1, then this B number to the S, if that is equal to B number to the T, then S has to equal T. Now, this if and only if is just a really fancy math way of saying this transformation works both ways. So if I have b to the s equals b to the t, I can say, therefore, s must equal t. But also, if I have s equals t, then I can say b to the s equals b to the t. So if s or t has a logarithm in it, then I can use an exponential on both sides of the equation to cancel the logarithm. So in certain situations, we're actually going to use this setup backwards. But for right now, we're going to see like this. 5 to the ugly algebra equals 5 to the weird algebra, but they're both 5s as exponential bases. So the powers have to be equal. So I'm going to write the equation. So we have 5 to the 6 minus 6x equals, and then I'm going to leave a little bit of space, and then 5 to the 7 plus x. So our one-to-one property of exponential functions, like we can just as the next line be like, yes, clearly, therefore 6 minus 6x must equal 7 plus x. And this is like what the book will do, and this is what some of the AI engines will do if you ask them to solve this problem. And it's not wrong, like we can absolutely make that logical jump. But what's going on behind the scenes is we're using the inverse of the 5 exponential. So the 5 exponential's inverse function is log base 5. So if I apply log base 5 on both sides, then log base 5 of 5 to the something just leaves us with the something because those inverses cancel out. The same thing on the other side. So that's another way to see that the two exponents have to be equal because we've got the log base 5 on both sides canceling out. All right, now that we've made that move to our next statement, now we've just got a basic algebra equation that we're solving. So I'm going to minus the x. So now I'll have 6 minus 7x's equals 7. And then I'll minus the 6. So negative, negative 7x equals 1. And then I divide by negative 7. And we get x equals negative 1/7. So apparently, if I take the number negative 1/7 and shove it into that original equation in place of x, that is the value that makes the equation true. And that's the only value that makes that equation true. So we just type in negative 1/7, and it says, yes, perfect. But sometimes I'll get equations where they don't start as the same base. So we got to make a little bit of a tweak to this. So I've got my 5 to the negative of x plus 3 equals. Now, what do I know about 125?
5.
Yep, it's 5 cubed. So I think of it as like a $1.25 is 5 quarters, but a quarter 25 is 5 squared. So that's 5 cubed. And now they're both written in terms of base 5. So now when I tack on my log base 5, I just get the negative of x plus 3 equals 3. Now, more than one way to solve the equation here. But since that x inside doesn't have anything multiplied to it, what I'm going to do next is divide by negative 1. We could turn that into a -1 and distribute it through as well. But now this will be x plus 3 equals negative 3. And it can be really tempting here. We see the positive 3, we see the negative 3. It's like, ooh, those cancel out to 0. But they are not on the same side of the equation. So focus on what do I need to do to get x by itself? I'm adding 3, so I'm going to subtract 3. And yeah, they don't cancel. I get negative 6. So when x is -6, if I take -6 and plug it into that equation, that's the only value that makes that statement a true statement. All right, now our next one's a little bit weirder. I've got 8 to a power equals 16 to a power. Now I know 16 is 8 times 2, but I can't write 16 as a power of 8, and I can't write 8 as a power of 16. Not with like nice powers I know off the top of my head. But what do 8 and 16 both relate back to? Yep. They are highly even numbers. They are just a bunch of twos being multiplied. So a bunch of twos in a trench coat. So the 8 is the same as 2 to the third. And then 16 is one more 2, so 2 to the fourth. So now they're both written in terms of base 2, but it's not 2 to an algebra expression equals 2 to an algebra expression. Right now, I've got 2 to a power to a power. So I need to clean this up before I can use my logarithm to cancel out the base 2's. So when I have 2 to a power to another power, what happens with the powers? Yep, they multiply. So I think of it as they're close enough to multiply. The only thing between them is the condom of mathematics. So we get 2 to the 3 times x plus 2 equals 2 to the 4 times x plus 1. Now I can use the log base 2. So I have 3 times x plus 2 in parentheses equals 4 times x plus 1 in parentheses. So now we just distribute. We have 3x plus 6 equals 4x plus 4. All right, so if I minus 3x, 4x minus 3x will leave me with x. And then I'm lazy, so at the same time, I'm also going to minus the 4. So I end up with 2 equals x. So questions so far on how these equations are shaking out. All right, now another one. Find the solution of the exponential equation, but with a fraction. Gee, thanks. All right, so 64 and 16. Is there a number that both of those relate to? So 64 is 8 squared. 16 is 8 times 2. Yep. So they are both powers of 4. Now, because they're powers of 4, they're also powers of 2. So if you didn't notice the 4s right away, they're both highly even. So you can write them all in terms of powers of 2 as well. And you'll still get the same solution. It just makes the numbers a little bit bigger in the solving. But we see the 4. So 64 is the same as 4 to the third power. And then I'm going to write the negative of 3x plus 4 equals the 1 over 16. 16 is 4 squared. So the 1 over 4 squared, like that was our hint over here, we can rewrite this as 4 to the negative 2 because we do need the 4s to be on the same line. I can't have 1 on the bottom of a fraction in order to use my log property, my 1-to-1 property. Now on the left side, I've also got to clear up this 4 to the third to the negative mess. So those are going to multiply. So I've got 4 to the, so the 3 times, that's a negative 1 times the 3x plus 4. So I'm going to write that as negative 3 times 3x plus 4 equals 4 to the negative 2. So now when I apply that log base 4, I've got negative 3 times 3x plus 4 equals negative 2. All right, now we distribute. So negative 9x minus 12 equals negative 2. Add the 12. So negative 9x equals positive 10. Divide by negative 9. We get negative 10 divided by 9. All right, so we've seen a whole lot of different bases. And then this next one is like, oh, how about a base E? Sure. So remember, E is just a mathematical constant. It's 2.718, blah, blah, blah. It goes on and on like pi does, irrational. But it's still just a number. So go ahead, write this one down, try it out. So that is E to the Z plus 4 equals 1 over E to the 2Z. 2 z. . 2 z. 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 2 Poof. So if you wrote log base E instead of natural log, that's fine. Like it still works the same. But ln is just our shorthand writing for log base E. And then we manipulate and we end up with -4/3. So even when the base is some weird number with decimals, as long as it's the same weird number, we can still solve the equation. So what question do y'all have on how these exponential equations have worked so far? All right, so we just did 5 examples where we could rewrite the equation in terms of the same base and then cancel the bases out. So it's real tempting to think like, oh, so this is what always happens with exponential equations. No, in fact, this rarely happens with exponential equations, but in math land, we like to do exponential equations like that first, just to get you used to thinking about how the exponents are working. But the reality is, most of the time when we're solving an equation, there isn't an easy way to write one number in terms of the other. So when this is the case, we have to use logarithms. And unless something has a base 10, we typically are going to use natural logs to solve. WebWork also specifically requests natural logs. So that's what we're going to do with this nonsense. So 5 to the 4 minus x equals, leave some space, 2. This is the question that I put on the final. So your homework, though, is going to look very similar to the amplify. You're going to have a whole bunch of equations where you can rewrite it in terms of the same base. But this equation where you can't write it in terms of the same base, this is what I put on the test, because this is the way it will look if you have to use this skill in chemistry, in physics, statistics, engineering. Like, you need to know how to do it when you can't make it look pretty. So no way to write 5, so it's the power of 2. No way to write 2, so it's the power of 5 without using some weird decimal. So I'm going to apply a natural log on both sides of the equation. Now, when we do that, it's the natural log of the whole entire side of the equation equals the natural log of the whole other entire side of the equation. All right, now there's a log property coming into play here. So if I had like the natural log of x to the 4th power, what does the log do to the power? Say it again. Yep. It takes the power and moves it down out front. So this would become 4 times the natural log of x. That's logarithm's whole purpose in life is to take powers and move them down onto the line. That's why we need to use the logarithm here. In the original equation, that x is an exponent. I can't manipulate the exponent right now to solve it. I need it on the line before I can start manipulating things. So our log property here is going to take this whole power and bring it down out front. So we're going to have 4 minus x in parentheses times the natural log of 5. And then this is equal to the natural log of 2. Now, natural log of 5 and natural log of 2, those are things we can type on the calculator. So that means these are numbers. They're ugly decimals, but they're just numbers. So if I have 4 minus x times a number, then I can distribute that number through the parentheses. So I'll have 4 times the number natural log 5 minus x times the number natural log of 5. And then still equal to natural log 2. So now we're just trying to get x by itself. So there's some stuff really close to x that's being multiplied to it. And then there's that 4 natural log 5 out front. So I have 4 natural log 5 minus the x term. So I need to cancel out the 4 natural log 5 with addition or subtraction. So since it's positive, I'm going to subtract 4 natural log 5 from both sides. Now, natural log 2 and 4 natural log 5 are not like terms. So we just leave those as they are. All right, so we've almost got x by itself. We've got this minus sign in front and this natural log 5. So this minus sign, I can sneak in there a 1. So this is negative 1 times x times natural log 5. So I've got more than one thing being multiplied, but I can still divide by both of those things. So that leaves us with x by itself. And then our direction said to round to 3 decimal places. So this is a crazy mess I can type on the calculator. Now, this question in WebWork actually asks for us to just type in that crazy fraction there, and that's the answer WebWork wants. But we can also get the decimal. Now, when we go to type this in, our natural log or our log, when we type that button, the calculator automatically opens a parenthesis. So we need to make sure we close those little parentheses in all the appropriate spots. Now, most of y'all's calculators, there's like a fraction button, so you can type this in so it appears like a fraction. But if you've got an older one, that may not work. Like my phone calculator doesn't do that. So for me to type this in, I've also got to put a set of big parentheses around the top of the fraction and the bottom of the fraction. So I start with my open parentheses, then natural log 2, which opened, so I closed the little parentheses. minus 4 natural log 5, close the little parentheses. And then I also need to close the big parentheses. Now I'm dividing this by, open parentheses, -1, natural log 5, close, close. So I get 3.56932. They told us to go with 3 decimal places. So that is 3.569. So if I plug in 3.569, 4 minus that is like 0. What, 4307? So 5 to the 0.43 is roughly 2. So you've got 2 examples in the WebWork homework that'll give you non-common bases to practice with. In fact, let's go find one in the WebWork. Now remember, all the WebWork is open right now. It's going to close on May 6th, which is a week from Wednesday. All right, so go ahead and write down the equation. We have 2 to the 2x minus 2 is equal to 3. All right, so I want you to try this one out on a sheet of paper. right, so let me flip the share. So here's what I got after working it out. Now, I will say the directions here for WebWorks say type an exact solution in terms of natural logarithms. So we had to use natural log when we were solving. And then what it is wanting for the answer to be typed in is this. This is what we mathematically call the exact solution. The decimal is actually an approximation, even though in every other field, when they say give the exact answer, they mean the decimal approximation. Now, if we had done it with log base 10 instead of natural log, our decimal answer would be the same, but our fraction answer, we'd have logs instead of ln's everywhere. And then WebWork isn't translating between those two easily. So that's why it's saying specifically to use natural logs. It's just WebWork being weird. So what questions do y'all have on how this played out? How compared to the work you did? Like, did you see something weird happen in your work that looks different in my work that you want to ask about? Either. Because on the exam, if you use log base 10 instead, that's fine. Like I'm gonna look for the fraction, but if you write the decimal after that, that's fine. So yeah, this is one of the 10-point problems on the test. All right, so our next one is another one that we can't write. It's got 4 to the x equals 5 to the x. So I can't turn 4 into 5 or 5 into 4. So let's go ahead and try solving this one. Four to the x equals 5 to the x. If we split the fraction into two different pieces, yes. And then the fraction would just look a little bit different. So we'd have natural log of 3 over 2 ln 2, and then next to the fraction plus 1. So you can't just like straight cancel it. You'd have to split the fraction to do the canceling. All right, did anyone get an answer yet? So I did a whole lot of fancy math work to end up with a snarky answer. But if we look back at the original question, 4 to the x equals 5 to the x. If we think about like those graphs, like the 4 powers are all different from the 5 powers. But there's one spot that all exponential, basic exponential graphs go through. And that is the point 0, 1. So when I plug in the 0 power, 4 to the 0 is the same as 5 to the 0 because they both equal 1. So 0 is the only number that makes this equation true. But solving the equation algebraically to prove 0 is the answer, like if you didn't notice it, the work is a little on the weird side. But we use the log, we bring the x's down, and now I've got an x on both sides. In order to solve for x, I have to get all of my x terms onto the same side. So I minused the natural log, the x natural log 5 over to the other side. So I've got those two terms. And then when I minused that, that leaves me a 0 on the right. So it's very rare for us to end up with a 0, but it can happen. Now, both of these terms have an x in common. So I factored out the common x. And my leftovers were natural log of 4 minus natural log of 5. And then that's x times natural log 4 minus natural log 5. So I divided both sides by that, but 0 divided by a number is just 0. And this is what can happen when you're doing math is you get so like focused on doing all the steps to the problem, and then at the end you get an answer and you're like, that seems way too simple. Go back, look at the equation, plug in the number, and see if it makes sense. And like once you plug it in, 4 to the 0, oh yeah, that's 1. Oh yeah, and 5 to the 0 is 1. Yep. Yep, 0 totally works. Let's see. And then after that, what we have is log equations. I'm going to leave the log equations for next week. Because we've got 2 days next week that we can split between solving all the log equations and then starting to work on the final exam review. So we should end up with 2 days for final exam review. All right, so let me hit the